everybody. So today we're continuing on with covalent bond formation. And we're going to start off by looking at the different types of bonds that we'll have. Now we've already talked about the nomenclature, but we haven't seen the actual formation of the bonds and the sharing of the electrons. Because remember, that's what covalent molecular bonding is all about, is sharing electrons. So the big thing that you're going to notice that's different today with seeing these covalent bonds is you're going to notice these lines. And these lines actually represent a pair of shared electrons. And by pair, how many do I mean? I mean two. So two shared electrons will be represented every time you see a line in a structure like this, right? So each one of these lines, 4 lines, represents a shared pair of electrons, okay? We're going to see 3 different kinds of bonds. A single, a double, and a triple. So they are exactly what they sound like. A single is where one pair of electrons is shared, all right? So for these, you're going to see a single line at each point where electrons are shared, one single line. The example here is methane, and that's CH4. A double bond has 2 pairs of electrons shared, and for a double bond, you're going to see 2 lines, right on top of each other, right? So this is 2 pairs of electrons that are shared for a total of how many electrons? 4 electrons, right? 2 here and 2 in that bond. Our example there is oxygen. Remember, it is a diatomic, so oxygen is never by itself. It's either bonded to a different atom or to itself, right? So just not as one atom, but as a paired diatomic with 2 atoms. And then our triple bond is the third one we'll see for covalent bonding. And just like it sounds, this is where we have 3 pairs of electrons being shared. Following the trend, we have 3 lines here. So right on top of each other, 3 lines between these 2 nitrogens, these 2 nitrogen atoms to make the molecule nitrogen, or N2. Each one of these lines, again, represents 2 shared electrons for a total of 6 shared electrons right there. Now, double and triple bonds are a little bit unique in that they're only going to form when we have diatomics of oxygen or nitrogen, or when we have carbon in the covalent compound. Okay, so it has to have carbon or diatomics of either of those 2 over there for it to have the possibility of having a double or triple bond. That's the only time that we'll actually see those. Now, before we will move on to the Lewis structures of molecules, I want to make sure that you remember the Lewis structures of ionic bonds so that you can see the difference, okay? So just a quick refresher, for Mg and Cl, we have Mg with its 2 valence electrons paired on the right, and we have Cl, I already drew in the 2 Cls because we're going to need 2 Cls, with their 7 valence electrons each, okay? So one of these electrons is going to go here. I'm going to draw the arrow to show that that electron from magnesium is moving to chlorine. It's being taken, or given, I guess. And the second one is going to go to the second chlorine. And on the other side of our arrow, what's happened is that magnesium has lost its 2 valence electrons, but it has a 2+ charge now, because it has 2 less electrons. And chlorine has gained that extra electron. So the chlorine has 8 total valence electrons, and there were 2 of them. So I put a 2 here. Because they each gained 1 electron, they each have a 1- charge. They don't have a 2- charge because they only gained 1 electron, okay? And then when we're writing the formula, we see 1 Mg, and we see 2 Cls. So the formula would be MgCl2, okay? So that is kind of starting us off with our covalent bond formation. Let's take a look at drawing the Lewis structures now that was ionic bond formation. Here is the Lewis structures for molecules, okay, so for covalent bonds. Now, we're still going to use the octet rule. That hasn't gone away. Atoms are still trying to have the electron configuration of a noble gas with 8 valence electrons, so we are still going to be using that octet rule. It's very important. So here's the steps for drawing the Lewis structure. You're going to start by counting the valence electrons. So you'll be given a compound like this, NH3. You want to count the valence electrons. Well, let's do it. I have 1 N here in NH3, so I'm going to write N1. How many valence electrons does N have? All right, if you look on the periodic table, it's in group 5 or 15, so N has 5 valence electrons. 1 times 5 gives you 5 valence electrons coming from N. We have 3 hydrogens, right? H3. So hydrogen, I have 3 of them, And each hydrogen, they're in group 1, right? So 1 valence electron, 3 times 1 gives you 3, for a total of 8 valence electrons, okay? So now we have our count. This is the number of valence electrons we need to show in our Lewis structure. Now we're going to draw the Lewis structure for each atom and draw lines to connect the electron pairs. Remember, the lines, right? 2 electrons is represented by 1 line. If you have double line, that's 4 electrons. If you have triple line, there's 6 electrons. But lines are going to connect the electron pairs. Okay, so it's kind of like connect the dots, if you will. Here's my Lewis structure for nitrogen, again with 5 valence electrons around it, and my 3 hydrogens, each with 1 valence electron. And I'm just going to connect the dots between lone electrons. This electron on hydrogen is lone, and so is that one on nitrogen. This one on hydrogen, and that one on nitrogen. This one on hydrogen, that one on nitrogen. And now we've connected so that none of these are lone electrons anymore. Okay? The central atom, this is key, the central atom, when you're drawing, like when you're figuring out how to do this, should be either carbon or a lone atom. So if carbon is there, carbon's in the middle, kind of like here. Or a lone atom. Carbon is not involved in NH3, it's not one of the atoms. And so the lone atom is nitrogen. There's 3 hydrogens. Nitrogen's all alone. So nitrogen goes in the middle. There's only one of it. Okay? Then we're going to take the free or non-bonded electrons to remain as lone pairs, if we need to, right? In this case, we might not actually need to. So we're going to draw those lone pairs as 2 electrons. You never draw just one, or we're not going to ever be drawing just 1 electron. We will draw electrons as pairs, okay? Let me go on to the next one, and then we'll see. So we're going to draw the revised actual Lewis structure and count the total electrons. So this is a little messy. I want to draw a little bit neater, and so I'm just going to draw the lines straight, basically, okay? And not showing those, like, electrons that make these up. I know a line is 2 electrons, so I don't need to show the electrons there. So let's count them. All right, so it says count the total electrons, both bonded or free. So right now I have 2, 4, 6 electrons, but I should be showing 8. Well, let's see which ones of these are happy. Which ones have their full valence? Hydrogen only needs 2 electrons to feel like it has a full valence. This one has 2, right? It feels like it has 2 because of those 2 bonded electrons. This hydrogen feels like it has 2. This hydrogen feels like it has 2. All those hydrogens are stable. They have a full valence. But nitrogen needs that full octet. It feels like it has 2, 4, 6 electrons. We're going to add on 2 more as a lone pair. So this one actually is going to have a lone pair. We add those on as lone pairs. Now we count our total electrons. 2, 4, 6, 8. Is it what we thought we should have, like what we calculated we should have for our total valence electrons? It is, so we're done, okay? The key here, when you count those total electrons, both the bonded and the free, they should match the valence electron count from step 1, which for me here was 8, okay? Now let's take a look at this second one, carbon dioxide. Now, if double or triple bonds are involved, we will not make you draw them. We will give you the structure already. So here's the structure for carbon dioxide. All we have to do now is add on any lone pairs that we need. Okay, so let's follow the instructions. We're going to, step 1, count the valence electrons. Well, I have 1 carbon, so 1 carbon. And each carbon has 6 valence electrons because they're in group 16 on the periodic table. 1 times 6 is 6. I have 2 oxygens. Each oxygen, oh, sorry, I meant carbon is in group 14, my bad. So it has 4 valence electrons. Oxygen is in group 16 with 6 valence electrons. 2 times 6 is 12. So I have a total of 16 electrons that I need to show. Here's the structure that's already been given to us. So draw the Lewis structure for each atom. It's already been done. The free electrons will remain as lone pairs. Okay, so we need to figure out how many lone pairs are there going to be. How many electrons am I showing right now? 2, 4, 6, 8. How many should I be showing? 16. Well, let's see. Is carbon happy, quote unquote happy? Does it feel like it has a full valence? 2, 4, 6, 8 electrons around carbon. Yeah, it feels like it has a full octet. Oxygen, however, each of these oxygens only feel like they have 2, 4 electrons. So we need to add 2 more lone pairs on each oxygen. We're going to add them so that they're spread out as far away from each other as they can be. So one pair I'm going to put diagonally up here, one pair kind of diagonally right there. Over here, same thing. Remember, electrons are all negative, so they don't want to be near each other. They're going to repulse each other. So we're drawing them kind of far apart as we can, but we're drawing them as pairs. 2, 2, 2, 2, okay? Now, each oxygen feels like it has 8 electrons around it. 2, 4, 6, 8. 2, 4, 6, 8. For a total of 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, which matches what we thought we should have, okay? So there's the Lewis structure for carbon dioxide. Now, once we have the Lewis structures, what we're going to do is look at a couple different things, and those are geometry and polarity. Geometry, if you think back to math, is the shape of the molecule, and polarity I'm going to get to in a second. So geometry comes from what we call the Vesper model, the valence shell electron pair repulsion model, okay? It's a long way of saying that the geometry around a central atom, the central atom is key, for a molecule or a polyatomic ion, but we haven't seen those yet with geometry, or we won't yet. So it will be based on electron repulsion. Again, electrons are negative. They want to repulse each other and be as far away from each other as possible. So that will create a certain shape that the molecule will take on when those electrons get as far away from each other as possible. Now, this chart is on the back of your periodic table. And we'll look at this in class, but this is kind of an abbreviated version of how to tell what the geometry of a molecule is. You look at the number of atoms bonded to the central atom, and how many lone pairs are on the central atom, and that will tell you what the geometry is. In class, we're going to do a model lab to see what these shapes actually look like, so just right now, know that this is a shape. We'll see what those look like next class. So here's an example. We're going to pick a central atom, so I'm going to pick this carbon, and we need to figure out how many atoms are bonded to it. 1, 2, 3, 4. Okay, 4 atoms are bonded to it. Are there any lone pairs? There shouldn't be. No lone pairs. So this shape is tetrahedral around this carbon. So that carbon, the shape is tetrahedral. Around this carbon, I have 1, 2, 3 atoms bonded. So I come down to 3. Any lone pairs? No, I don't see any lone pairs. So 3 atoms bonded. No lone pairs. This is trigonal planar. So that carbon right there is trigonal planar. Down here, let's look at chlorine, right? So that's technically the center because hydrogen can't be the center. It can't have a full octet. So chlorine's in the center here. How many atoms are bonded to it? Just 1. Here's 1. How many lone pairs are around it? There's 1 pair, 2 pairs, 3 pairs. So 3 lone pairs. This is linear. No matter what, this would have been linear with only 1 atom attached to it. Now the last part of it is looking at polarity, and this is how the electrons are distributed in the molecule. Are they evenly distributed or not? Is part of the molecule pulling the electron stronger to it? This is important because it's going to determine intermolecular forces and bulk scale properties like boiling point, melting point, solubility, surface tension. We're going to get to see those in a couple of classes as well. In order to tell if a molecule is polar, we're actually going to look, yes, for the uneven distribution of electrons versus for nonpolar, the even distribution of electrons. But the hint here is that, is it a mirror image? That's how we actually tell the easy way of seeing, is it polar or is it nonpolar? And again, this will come up when we're looking at properties of molecules. So look at this. This is H2O. Is it a mirror image left and right? Yes. Is it a mirror image up and down? No, it's not. It has to be a mirror image both ways for it to be nonpolar. So this is not a mirror image up and down, therefore it is polar. The electrons are unevenly distributed. Right here, this is a mirror image left and right, and up and down, therefore it is nonpolar, and the electrons are evenly distributed. Let's try this one. So let's look, is this molecule a mirror image left and right? Yeah, it is. Is it a mirror image up and down? No. Or sorry, yes it is. Sorry, this one is. Right? Up and down, it is going to be a mirror image. So this is non-polar. And over here, is it a mirror image left and right? Kind of. Up and down? No, because this fluorine has no corresponding fluorine down there. There's an uneven number of fluorines. So this is polar. All right? We'll see more of that in class so we can practice in the model lab.